Okay, let's start the crash course for principles and techniques. And this is going to be a ride. Alright, so here's how it's going to go today. First, we're going to discuss Bayesian networks, everybody's favorite faculty. Then we're going to talk about maximization of likelihood. And then my friend Max is going to teach you all about decision problems, which you should probably have done in reinforcement learning, but that's not the point. That is not the point. Okay. But before we start, after we're done with the, most of the theory, we are going to have a break, then questions about whatever you are confused about the course, and finally, we are going to do some practice exercises if we still have the time. Right? Any complaints? No complaints. Perfect. Let's start. Now, I'm going to give PTSD to everybody who failed probability theory last year, but yeah, probability theory. You probably know the formulas already. If not, you probably should know the formulas already. Do you have any questions about any of them? And by questions, I mean, why are they like this, or where do we use them? Any confusions? No confusions. Perfect. Then we're gonna quickly go through them. I mean, to the most important ones. I wish I had a pointer, but I don't. So, we have the product rule. I think everybody knows this one from the, what was it? Variable elimination thing? I think that was the one. We have the conditional, not conditional, joint probability, and how it can be rewritten. Conditional probability, still from the variable elimination thinking. Now, joint probability and conditional probability, it bears to repeat this. These are different. They're not the same thing. So don't make that confusion. So joint probability is just technically gathering multiple variables together. Conditional probability is picking another table entirely and calculating probabilities from that. Okay, so they're kind of two completely different probabilities. Right, and independence and conditional independence. It bears to mention that the difference between independence and conditional independence, there is a conditional probability there. But technically, you can look at these two as two completely different probability distributions. Right, there's nothing related between these two. That's why they make the difference in naming. Any questions about independence or conditional independence? Yeah.
Did you have questions about proving independence between variables on your exam? Because I saw it's in both of the example design that they provide us.
Yes. Well,
so it's a must.
It will probably appear either here or when you go to graphs, like Bayesian networks, you're going to have a type of graph that is going to ask you, okay, are these variables independent given this variable? And you're supposed to recognize a pattern there and say, no, they're not, or yes, they are, because of this. We're going to get into that. But yeah, you probably will have to prove independence, which you can do in two ways. One, by proving one of these formulas, or two, by showing, okay, this is my Bayesian network. Because this thing is observed, this and this become independent because this is this kind of connection. I'm going to show them in the next slides. Okay. Any other questions about independence? No questions. Perfect. Next. Yeah, now here we're going to have fun. Well, as I mentioned before, Bayesian networks are one kind of graph, a directed graph. But that graph has some properties. Let's get into them. First, I'm going to say that if anybody remembers surjective, injective, bijective functions from mathematics, these things are kind of similar. As in, a DMAP basically says if anything is independent in the distribution, it's shown as independent in the graph. Okay? An IMAP shows if anything that's independent in the graph is independent in a distribution. And PMAP says, okay, basically both of them taken together. So if something is independent in the graph, it's independent in the distribution, and vice versa. So basically, DMAP says that if something is independent in a distribution, it will be represented as independent in a graph. IMAP says everything I represent as independent in a graph is independent in distribution. And PMAP says that I took into account all of these situations. So basically, whether I look at distribution of the graph, I'm going to arrive at the same conclusion. Now, this is only important because this is a property of Bayesian network, so it should be of a well-made Bayesian network. Any questions about this? No questions. Perfect. Next. Now, I mentioned before, you might be asked something similar to this. So, there are some, shall we say, patterns in a Bayesian network, and I have names for them because they happen so often. Let's go to them. Causal chain. Well, technically, blood pressure is related to age, right? Because the older you get, usually the worse your blood pressure. But that's not because the older you get, automatically your blood pressure increases, right? It's not some magic like that. It's because your weight is usually tied to something else that's tied to your age, and that's why technically as you age your blood pressure gets worse, because your weight gets worse, which makes your blood pressure get worse. Which is why in a causal chain, if the thing in the middle gets severed, so observed, age and blood pressure become independent, conditional independent, which basically tells you that, okay, if I know your weight, I don't care about your age, it's not going to tell me more information about what your blood pressure is. That's the important part of causal chain. And that's also the important part in Markov chains. Okay, so like that very long chain. They work on the same principle. If you observe something in the middle, everything in the past doesn't matter because it won't tell you anything more about that situation than what you already know. Any questions about causal chains? No?
Not for causal chains, but can I go back just for one question to the IMAPs? Given that Bayesian networks are called IMAPs, the distribution, it means that some variables in the Bayesian network that are marked as dependent, there is an arrow between them, might not be dependent on the distribution, or they get it wrong?
If you look at the IMAP, it says that everything that's marked as independent in the network is independent in distribution. So basically this assumes that you caught all dependencies in your network. But here's the problem. It's quite impossible to account for all possible independence and dependencies in reality, right? Because there are some things that happen so rarely or just once, and it will still cause two variables to be dependent, but it wouldn't matter that much. So it's basically a Bayesian network is always a best guess or a best approximation. That's going to appear multiple times in Bayesian networks. You can never be certain when you work with probability. You can just approximate enough that the possible error is small enough to not matter. Right? That's why a Bayesian network, like an ideal one, would be a PMAP, but you will never get to that, pretty much.
Yeah, I can memorize the saying that if something is independent in the graph, it's independent in the distribution, but I'm having a hard time visualizing the opposite case, what it says about the dependencies.
Well, okay, so let's say to prove that something is not an IMAP would basically mean that you mark something as independent in your graph.
So there is no arrow.
No, independent in our case could either mean, let's say, a common cause, a common effect, for example, right? So you assume burglary and earthquake can both cause an alarm, right? So these are, you consider them independent. But let's say we live in a world that a burglary happens every time an earthquake happens, right? Then they wouldn't be independent. So this would not, this model, if this was your model, it wouldn't track, it wouldn't be correct for that world. So it wouldn't be an IMAP. Now, let's take the opposite case. Let's say we don't live in that world, we live in our world where there isn't a correlation between burglary and earthquake, right? Now, if my model said that burglary and earthquake are dependent, then it wouldn't be it wouldn't be a DMAP, right? Because I marked something as dependent, which in reality is independent. which is the reason why DMAP and IMAP always mention a probability distribution. So basically, you can only define a IMAP and a DMAP based on a probability. So based on what you already know your data. Based on that, you can define a DMAP, an IMAP, and a PMAP. You can define it on a generalization because you can't account for all possibilities. Make sense? Somewhat?
Very big things.
Now, let's go to common cause. So basically, when we have let's take this example with a train strike, Martin being late and Norman being late. Now, if you only take Martin late and Norman late, obviously they're not related to each other because unless they live together, it doesn't matter if one is late, whether the other one is late, right? But if I observe that their common cause has happened, so a train strike, then they're not independent anymore, right? Because if the train strike happened and Martin was late, then probably for the same reason, Norman will be late as well, more often, right? So they're no longer independent because I know that something happened in the past and something happened with one of them, which tells me information about the other one. That's basically how this one would work. Yeah.
But wouldn't they still be independent? They would just still be both dependent on the train strike?
Okay, let's move on to another example. Let's say, for example, two people are allergic to nuts, right? That's the common effect. They encounter nuts, they're allergic, right? Let's say both are eating at the same place and they both get an allergy. Now, obviously, they can get an allergy from everything else because I don't know if they have other allergies or anything else, right? So technically independent. But now I know that the food served at that place had nuts in it. And I know one of them got a nuts allergy, right? So it's more likely that the other person also got their nuts allergy, not another allergy. That's basically how the common cause, common cause works. Does it make sense now? Yeah.
And if you know that there's a train strike, does that break the dependency between Martin late and Norman late?
No, it creates a dependency. Because if a train strike happened and Norman is late, then probably it's very probable that Martin will be late for the same reason. So it affects both of them. Because we know that they're both dependent on train strikes. That's why they're no longer independent. Yeah.
I think what you wrote there is correct, where if you know train strike, then they become independent. And if you don't know train strike, then they are dependent.
That's what I remember as well from the lectures.
And that's what's on the equation
Yeah.
as well.
Can you fix this, right?
So I think
Yeah.
it's true.
Can you take a look?
I will take a look.
How you guys revise that? Which is expected from Google Colab. I hate that platform.
No, they're conditionally independent given T, right?
Yeah.
So that is what
Oops. Go then. Yeah. The conditional value is 1, 2. Yeah. Back. They go them switch over. Right. The example is different. Fine. If the train strike happened, then I wouldn't get any more information. Fine. Let's move back. Alright, so the explanation will be the same, it's just that it will be for the common effect, not the common cause, shall we say. That makes them dependent, conditional independent. Moving back. Alright, so for the common cause, if I observe the common cause, then they're technically independent of each other. And for the common effect, if I observe their effect, then they're no longer independent of each other. Because if one thing caused the effect, then it's going to be caused by the other one, and vice versa, in some cases. Any questions about these ones? No questions. Perfect. Moving on. Now we're moving to the Bayesian network. Now, Bayesian networks are basically a way of representing dependence and conditional independence in graphical form so you can calculate them easier. And here's the important part. Each node has a probability attached to it, but it's not the probability of that event happening. It's the probability of that event happening given the value of its parents. And that's for every node. So basically this makes it easier for you to collect data in the real world because you cannot really collect independent data, right? Because everything is dependent on something else. But you can collect dependent data and then calculate the independent probabilities from that. That's basically the purpose of a Bayesian network. And well, at the basics, they basically use the joint probability formula, which splits it into conditional probabilities. Now, I assume everybody knows factors from the assignment, from the variable elimination assignment. Are there any questions or confusions about what factors are, how they work? No questions, no confusions, perfect. Then,
One question.
Yeah.
So let's say I have an observed variable. So I
Yeah.
want to compute something and I observe that A is true.
mm-hmm.
How would I write that in a factor? Because if I just do the probabilities, the joint ones, and with their conditions, then I would write the small a for the one that I have observed. How would I do with the factors?
So how would the factor as in the notation or the table of the factor?
The factor notation.
The factor notation. Well, exactly as you said. It's like when you have, how will I say? Right. When you have a probability distribution, when you have a joint probability, you have the variable, random variable for each one, right? Well, in the factor, you also write the name of each random variable, but for the random variable where you know what it is, you put an equal to its value. Right? That would be the easiest notation. Or in this case, you can also write it like this, but I would do it random variable equals to value. It makes it easier for the person to understand you got what it means. Now, factor product. Any question about this one? No question. Marginalization. This is basically just marginalizing a variable. So in our case, it would be the sum. In the probability course, it would be the summing of all possible cases for one of the random variables having a specific value, which would give you the unique factor. Now, it bears to mention, factors are not actually probability distributions until at the end when you normalize them. In between, they're intermediary values, and you cannot call them a probability distribution. That's why stuff like this can happen and they don't sum up to 1 in the table. Now, for reduction is exactly what we discussed. When you observe the random variable and you know its value, then obviously the other cases when that random variable doesn't have that value can be removed because they never happen. Which again would not make this a probability until you normalize it. Now, variable nature algorithm, I assume everybody's familiar with it. Yeah.
During the exam, would it be detrimental that we pick very nice elimination ordering? Does it need to be a specific one?
Well, if I remember correctly, in the assignment you had to use heuristics, right?
It was as a bonus.
Right. If not, then they probably will tell you, okay, pick them in this order, or pick them for this, because that makes it possible to grade it easier. But if they don't tell you, then the result is always going to be the same, technically.
Also, I think quite often what they say, at least in the exams that I've seen, is that they say do it in alphabetical order. And also, I mean, obviously there are specific orders that are worse. I mean that you will have to do more work. So I think it's quite likely that if they want to have a specific order, that they will tell you, and otherwise it doesn't really matter.
Okay.
Yeah.
In the slides, there's one heuristic mentioned. Do you have to know
Well, it would be a good idea to know it because it makes your calculations easier. Then again, it really depends on how they ask you to do the calculation. If they ask you to do it in alphabetical order, then obviously do it in alphabetical order. If they ask you to use a specific heuristic mentioned in the slides, then you'll have to use that one because everything that's in the slides and is marked as exam material is fair game for the exam. Usually the heuristics make sense though, like on principle, so they're nothing that confusing. They're mostly greedy methods. Any other questions about variable elimination?
About reduction and variable elimination, which part is actually reduction? Because I remember from assignment I was a bit confused about that.
Well, okay, reduction, if we go back, reduction is basically this one, okay? So you have some evidence, right? Because you want to compute a conditional probability, you need evidence. That evidence tells you what definitely will not happen, right? So what you can ignore in your calculations.
So reduction is basically having evidence.
Yes.
Yeah,
with
so in this case you have C1 as your evidence, and then you say, well, C2 definitely isn't consistent with my evidence, so I know that is not the case, but that also means that I can remove all the rows where I have C2, because I know that that's not realistic, that's not what is actually the case.
Then if we have a factor that only has the variable that is evidence, does that not count at all, or is that multiplied at the end with all the probabilities?
So if you have a factor that's not just the evidence,
Yeah, like in this case, if it was just a factor with only C, and you know that C1 is your evidence.
well, then you have a factor with just C equals to C1, which is basically gonna work in the same way, just that you're gonna only have the row with the C1, right? So when you do multiplication, you will not have to take a row, just that one. Now, the purpose of reduction should be clear, it's for you to account for evidence. The purpose of product is for you to be able to combine factors so you can do the marginalization easier, right? Because if you look at the factor product, you always have to have something in the middle that ties the two factors together. It doesn't have to be one variable, it can be a set of variables, but there has to be something they have in common for you to be able to do product. Right? And then marginalization is basically removing all the variables that don't matter for your query. So for example, if you want to know probability of A given B and C, you want to get rid of D, E, F and the other variables. That's how you do it with marginalization. Now, the order in which you do it makes it easier or harder, but you will arrive at the same result regardless. Okay. Any other questions for this one?
Maybe it's also good to mention that marginalization is usually after product, so you remove all the factors that you multiply.
That's what I mentioned. Yeah.
Kind of random, but do you have any tips for how to just reduce the amount of writing you have to do in terms of writing out the factors and everything to speed it up? Because I find it just takes a long time.
Well,
If there's any tricks you've seen
in the exam, to be honest, you shouldn't get factors that are big enough that how you write them should differ on the time, right? So you should have at most 4 or 5 variables, something like that. And how you write them, well, if you know the algorithm down cold, it shouldn't take you too long, regardless of how you decide to write them. And I think the way they write them in the course, where it's just the random variable and the observed value, with an equal, maybe if you want to also mention the name of the random variable observed, is fast enough. It also, yeah.
So let's say I have, I don't know, some observed variables and I want to compute the distribution of one variable. But usually you would, in the factors, always only of the factor variable have like the true cases, because the false ones you can get from 1 minus the probabilities, right? That's
Yeah.
how it always is. But then at some point they don't all sum to 1 anymore. So when do I add the false cases for the query variables? Because in the end I can't if I only have the query left, because they won't sum to 1, so I can't find it like that.
Okay, so first, in order to avoid this issue, yeah, they're given just the possibility of the true one, but factors don't have that limitation in the sense that you can just make another table for the false one as well, and then when you work through it, you will not have the false one missing. But at the end, when you normalize, well, normalization basically means you sum up all the things you have left in the table for your query, and you divide them by the total sum, so you get a probability, right? But in your case, if you get a probability that's like if you get a number that's like 0.5 or something, you can say, okay, this is for the true, and the false is going to be 1 minus this one. But again, it would be much better if you just write out all possible combinations of this one in a table to make it easier for you to
Also,
calculate them.
if you don't have binary variables, then it is so much easier to just write out everything.
Yeah, and there's no guarantee they're going to give binary variables in the exam. They might not give binary variables just to check if you understand factors work for any number of values for a specific variable, which is much better for you to get used to this one. And if they just give binary variables, then you don't have that much to write, right? So it won't make much of a difference. Any other questions about factors?
Yeah. Maybe a weird question, but in the algorithm, why don't we reduce first? Isn't that reduce computation?
Well, you do reduce first. If you look at these ones, the C for the write down is for you to write by hand, not for the algorithm to write, right? So this is for you to understand what you're supposed to do when you want to implement the algorithm. But the first thing you do in the algorithm, obviously, you reduce, right? Yeah, that makes sense. So you make the factors, and then you reduce all the variables for which you know the observation already. And you might have a special case where you have a factor for with just one variable, right? So let's say C, and C is observed. And you might worry because after you reduce, you're not left with no variables. Well, then you can just say, okay, I have a pseudo variable that's still gonna be C, but it has just one case, C1, and that's my table, just one line. And then you compute as normal. Make sense? Perfect. Okay. Let's move on to hypergraphs, which is just a fancy way of saying I have edges that connect multiple nodes. So in a normal graph, if you remember how a normal graph is defined, you have a list of vertices, right? A set of vertices. And you have a set of edges, which are basically tuples of two vertices and saying, okay, this vertex is connected to this vertex, etc. Right? That's a normal graph. A hypergraph is very similar. You still have a set of vertices, but for edges, you no longer have tuples of values, you have sets of values. So for example, you're going to have a set of value ABC, which is going to be, okay, ABC are connected by an edge, for example. That's the definition of a hypergraph. And in the context of a Bayesian network, you would have an edge, so like a hyper edge, for each probability table, so for each conditional probability. Now, I haven't actually seen this used in practice, if I remember correctly, but they might ask a theory question about them.
It may have been in an exam like 2 or 3 years ago, but I think it's just another way to explain what's going on.
Basically, a hypergraph can always be reduced to a graph, so as long as you don't get freaked out when they say hypergraph and remember what it is, you can just reduce it to a normal graph and use the same stuff used for a normal graph. I don't think it would be worth it to just work with a hypergraph instead of a normal graph. Any questions about these ones? No questions. Perfect. Now, here we have a problem. Now, what's the problem? But in reality, it's going to be hella hard to calculate all probabilities based on the whole network, right? It's going to be difficult. But what you could do, for example, if you remember in the case of Monte Carlo randomization, you could generate random samples, use them next to your network, and then calculate the probabilities in that manner. So basically, you calculate the actual value by doing a million randomizations, which, as you know, based on the central limit theorem, you will always arrive at your result given a certain error margin after a very large number of simulations. Now, let's take an example, because this is important. For simple forward sampling, let's take this network as an example, right? And let's say I want to calculate the probability of report given, well, leaving, right? Actually, let's say I just want to calculate the probability of report, right? Just that. That's all I care about. Now, what's the easiest way to calculate the probability? Counting, right? So imagine if you just had a humongous table and you had all possible options in whatever number they are. You just have to count, and there you have it. Probability of report is probability of all cases. No, probability of cases where report is true divided by probability of all cases, right? So probability of the number of cases where report is true divided by all cases. That's it. That's the probability of report. Now, the reason why you can't do this in reality is because you cannot actually count the probability, just the cases with report and nothing else. As we discussed, independence is quite hard in reality. But what you have the conditional independence and Bayesian network, so you can do simulations on the network and propagate the values you get forward. Actually, let's just give an example. Do I have a marker?
Yes.
Alright, so we have this network, right? And let's say I give you these random generated variables, which I absolutely would not ask for this, but that's fine. How many? 3, 4, 5, 6, 3, 4, 5, and let's say 0.02 for the other one, okay? Now, this, as you see, as you will probably notice, wouldn't work as values for random variables because they're true or false, right? Obviously. But here I'm going to say the convention that true is always bigger than false. So when for example, let's say probability of tampering, right? Well, the probability of tampering is 0.02. So the probability of tampering being true is 0.02. So anywhere up to here, so if my random value falls anywhere up to here, then it's false, right? Anywhere up to 0.98, it's false. If it falls here, for the last 2%, it's true. Right? Would that make sense? That would make sense. So, can anybody tell me, in my case, if tampering is true or false?
False.
False, right? Because it falls, somewhere around here. Doesn't matter where. So this is false. Okay, perfect. Now, let's take fire for the same principle. Is it true or false? False, right? Now, let's take the probability of smoke. Well, do I know the probability of smoke? No, I don't, right? But what I do know is the probability of smoke given fire. Now, normally, the whole table here would also contain a probability of smoke given not fire. Actually, I have it. Never mind, I'm blind. Alright. So what's the probability of smoke given not fire? 0.01, right? Now, I am in this case because I know that fire is false. And the value for smoke would be this one, 0.6. So is smoke true or false in my case? False, right? Because the probability of smoke given fire to be true is 0.01, which means that anything up to 0.99 is false. So this one will be false as well. Now, for alarm, I want to take the case where tampering is false and fire is false, which is which one? The last one, right? Okay. I have this value, because again, generating them in order. So what's the value for alarm? False, right? Still false. And then I have leaving, which, what's the probability of leaving when the alarm is false? 0.01, right? So leaving is also going to be false in my case. And what's the probability of report if leaving is false? It's the last one, right? 0.01, which would make it false as well in my case, right? Now, this is how forward sampling would be done in a network. right? Because in the slides they don't really mention how it's done, they just say, okay, this is what I get at the end. So you start from the variables that are completely independent, so these two. You take the random value they were given. You yeah.
What is that like the one that you just
Yeah.
circle around? What are those values? Where are they coming from?
Well, if you were to look at the slides, they see you generate them randomly. But in order for us not to lose our minds, you have to have some conventions. Okay, the first convention, as I mentioned, is that I always assume that the zone for true is after the zone for false. The second convention is I'm trying to generate values between 0 and 1. Now, this is not a requirement because I can always scale back the values so they are between 0 and 1. It's just that if your probabilities are between 0 and 1 and you are going to use the scale between 0 and 1 to decide if it's true or false, then it would make sense to just generate them between 0 and 1, right? Now, in this course, they're generated randomly and that's how they say. In the next course, Bayesian statistics, you're going to learn that they're not generated completely randomly. You can make an assumption about the distribution. But that's outside the spec of the course, so we're not going to get into that.
So each time you run one simulation, then regenerate those values again. And
Yep. That's basically what they did in the slides. But they never actually, they didn't actually show you step by step what actually happens and how they distribute in the network. That's why we're doing it now. Now, is anybody confused about how forward sampling is done?
Is it possible that we don't have any independent variables, that they're all dependent on each other in a way?
No, because that would create, if I'm not mistaken, a cycle.
You just cycle that, right?
Yeah, so Bayesian networks are acyclic graphs. If everything was dependent on something, it would mean that everything has at least one arrow pointing to something else, right? Which would make it possible for you to create a cycle, which would invalidate the property of a Bayesian network. And if you think about it, in reality, there has to be something that's not dependent on anything. So for example, the mass of the atom is not dependent on anything else in the world, right? That's just a constant of physics. The speed of light is not dependent on anything else. So you can't have everything depend on everything else in reality. That's why you can take that property in a Bayesian network. Does that make sense? Any other questions about this one? Yeah.
Is it possible for the forward sampling to calculate not like posterior probabilities as well when you have evidence? And if you include the evidence, does it not just become rejection sampling or?
Exactly. We are gonna get into that, but you are completely right. That's why they exist. Because the problem here is that I assume that I know jack shit about everything, right? So I'm just calculating this stuff based just on Bayesian network and no outside information, which is not really that useful in the real world, right? Because you can just get that stuff just as easily by using variable elimination, right? So there would be no point for this stuff. It's just a nice way of doing it, but it's not a necessary way. Now I have one question before we move forward. What would happen if the variables were not binary?
You just have to impose an other ordering of the variables.
Yep.
Any ordering that we want and then sample by
Yeah.
that.
That's perfect. Exactly. That's what we'll do. So, if let's say for example that tampering has T1, T2, and T3. I don't care about the probability. Okay, let's say we have these three. Now, in our case, all we have to do is just, as she said, solve them, right? And then just define my zones, like I did for the binary case. And this zone is going to be T1, this zone is going to be T2, and this zone is going to be T3. And that's it. It works just the same. Yeah.
if we get exercise like that in the exam, will that be provided for us, or we somehow need to decide how the scale works? I mean, not how it works, but how to.
Well, they either will mention it, or what's most likelihood, that it's going to be binary, in which case they mentioned it, I think, in the slides, that true is always assumed to be more false than false. Do make sure to look in the slides again, but I'm pretty sure that's what they said in the slides as well. So that's what they would expect in the exam. Though, it really wouldn't, like, it would change the final result for that simulation, but it really wouldn't change that much for the final product, so I don't think they will deduct that many points if you just get the scale inverse. Especially if you mentioned, okay, I assume false to be true to be first and false to be second, I don't think they will deduct that many points or any at all. Because the point is for you to understand how forward sampling works, not to, memorize the scale by heart. Alright, yes?
So the thresholds on this line, are those like probabilities but then sum?
Yes. Because that's, it's like someone asked why we generate between 0 and 1. That's the whole point, because it makes, the probability is already between 0 and 1, so it makes much sense. Now, technically what you're doing here is making a marginal probability, so it's not t equals t1, but t greater than t1 or t2, right? That's how they're called, but they work in this manner. Okay. Any questions about this thing? No questions. Perfect. Now, as someone mentioned, what happens when we have evidence? Well, let's go to that first. When we have evidence, obviously we cannot just sample everything, right, to calculate the probability, because some samples, or most of them, will not be valid, right, because they go against our evidence. That would be useful. Now, there are two ways of taking this into account. First way is to just reject all the samples that are not in line with our evidence, right? Simple, easy, very inefficient, because say for example, your evidence only happens with probability 0.02%, right? So it happens very, very rarely. Now, how many samples would you be able to use out of a million? Just 0.02% of them on average, right? Which is not that many. Which make it much more difficult for you to approximate the probability, because whether you like it or not, when you generate randomly, you need a lot of simulations to get a result. So rejection sampling wouldn't work in practice, but in theory it's very simple, so it's given at the first example. And it's the most intuitive one, right? Just remove everything that's not in line with the observation. Any questions about this? Well, I have a question. How would we go about actually doing rejection sampling using the same process in forward sampling? Any ideas?
We still sample everything, and then let's say if our evidence was that fire is true, then we just remove all samples that have fire in it.
Yep, exactly. So for each case, we go through this process that I mentioned here until we hit something that goes against our evidence. When we do that, we will discard that sample, move on to the next one, which obviously makes it very inefficient, right? Because we do a lot of calculations pointlessly. Now, to move on to the point why this is bad, is because we have this inequality. Now, I will not go into detail about why the formula looks like this, because quite frankly that's not the point of the course. The point of the course is this. If you want to calculate your probability within a specific error, you solve this inequality, and that gives you the number of samples you need to get that specific margin of error. Now, why this is important? Because as I mentioned, when you do rejection sampling, you lose a lot of samples. So the number of samples, the number of actual samples you have to generate to get that number of samples you can use gets very, very big, which gets very, very computationally expensive, which makes it unviable for the real world scenarios. Right? Right. Yeah.
Do you have to know this inequality by heart?
Yes, they will probably ask a question that's going to be like, okay, I want this error rate, and I'm going to give you the symbol. What's the number of samples?
Okay.
Error rate will be the absolute.
Yes.
And what is the other number? The probability strictly less than
So
1.
the inequality used for number of samples is this one, right here, which is going to be so how many samples do you ensure that with probability less than 3? Okay, so this one is the difference, so it's the margin of error. This one is the ballpark where your probability should be, right? Because as we discussed, it won't be an exact probability, it's going to be a marginal probability. And this one is going to be the number of samples. So hashtag sample, that's the number of samples. Yeah.
So the evidence is given in a margin, or what is delta here?
Which one? This one or this one?
First one you pointed at.
This one.
Yes.
This one is the threshold for the probability, right? So the probability is never going to be bigger than this one, if I remember correctly. Yeah. So the probability of your actual probability being different by your real probability by bigger than this thing is going to be always smaller than this one. This one, right here. Which would be your theta, or how you call it. This is the general formula, and when you move it, you move it around here. But again, that doesn't really matter because they're not going to ask you what this means. They're just going to give you something of this manner, and they're going to be like, okay, what's the number of samples? And you're going to be like, yeah, sure, the number of samples is always bigger than 184, whatever the number is. That's how it works for the holding, for the this inequality. So my suggestion would be to just memorize. If you want to memorize just one thing, this one would be perfect because it gives you the exact formula. Otherwise, you can always go back into the slides and look at the proof of why this makes sense, which I think took half a lecture once, but you can have a look at the proof. But that's basically a way of telling you, a way of approximating how many samples you will need to get the result you want. Yeah.
So the right side is independent actually of the result we get from samples. It's just a number which will always be the same based on the delta value of the deviation.
Can you say it again?
The right side will always be the same based on the delta deviations of the other one.
What right side are we talking about? In the first line, where you check whether something is smaller than delta?
Because we compare the sample we have, right? The sample size was that, right? On the left side?
Yeah, what line are you talking about?
To the right side. From the right of the sample.
So this
Down,
or
this
this?
one, this one, this side.
Okay, so this one is always going to be the same, but the same in the sense that this one is how much probability you're willing to stomach, right? So for example, let's say I can only accept the probability of 0.05 that the error rate for my approximate probability is bigger than this thing, right? This thing is the actual error. So basically you have two parameters you're moving. You're moving how much risk you're willing to accept and how big the mistake is going to be for that specific risk.
So this is basically only dependent on the values which we can
Yes.
choose ourselves.
Now, why is it dependent on just these ones? You'll have to look at the slides for that, but yeah, basically yes.
And we compare the sample size, or what is on the left hand?
Then you compare it to the number of samples. So we say, if we have an acceptance probability where we say, okay, we want to accept something worse in only 5% of the cases, which is pretty similar to what you do in statistics. That is one thing. But you also say, well, because we're doing an estimation, we're never actually going to find the correct value, right? We're always going to be within an error margin. But we can say, well, that can be bigger or smaller depending on what you want to accept. So essentially that's what we say. Well, we say the more accurate we want to be, the more certain we want to be, the more samples we need to do. That is essentially what this entire thing is saying.
So it's kind of a power analysis, right?
Yes, I think so.
Yeah.
Why? In the beginning there is a minus out, right? And then there is a minus inside. There is a mistake, right?
So, no, it shouldn't be a mistake. It's just that from this formula to getting to here, obviously some manipulations have to be made.
But we want to know how many samples to ensure that the probability is strictly less than delta, difference between estimated and I mean, we just
But it's going to be the logarithm of a number smaller than 1, so it's going to be
but why are we taking the logarithm?
because it's exponent. So you have the
But-
exponent and you take the logarithm where it's going to be negative, so you add the negative, so that brings a positive.
We just want the right side of the very top equation to be smaller than delta, right? That's, I mean, we just add one more inequality on the right side. So that's basically what we do. So
No, it's the number of samples is not there in the first equation. It just says that it's the delta for the number of samples, but it's not delta times number of samples.
but I don't understand.
Alright, let's go to it by on the board.
So the hash rate sample is in the first equation. It's only on the left side, not on the right side of the equation. On the right side in the first
Okay.
equation is only
So,
the delta.
I think it would be easier if you just go for the steps. Alright, so basically what we're doing is this. First and foremost, we're going to define what that symbol is. So we have P approximated minus P actual bigger than this thing, in absolute value. Is equal to that random symbol that I never memorize what it means. Basically, our equation states this. Minus 2 times e to the power of 2 times I. And the number of samples, let's say we're going to call it n. Times n, 2 times n, times the error to the power of 2. Okay, perfect. But what I care about is the m here, right? So, first I'm gonna do this one, divide by minus 2, which is gonna move my, is gonna reverse my equation inequality to this.
I think you have the minus is in the exponent and not in the front.
It should be in the front if I'm correct. Can you have a look at the slides again?
Yeah, I am taking a look.
Yeah, in the very first equation there at the top is the -2 out front. But wouldn't that always result in a probability less than 0 if you evaluate the top equation? Sample is positive, epsilon is positive squared. Multiply that by -2, that you always get a negative probability. Does that make any sense?
Well, it shouldn't. Which means I'm mistaken the slides. It's fun. Ah, yeah.
What is the issue exactly?
For the half inequality, the minus 2 might have put it outside the equation again.
I don't know if this is exactly what it says in the slides.
Ah, that's perfect.
Google says that the negative is in the exponent
I know which one the slides are wrong.
in the second equation.
Seriously, the slides are with this?
Yeah.
Yep, the slides are exactly like this. Now, lovely. Okay, let's. This is lovely. Why?
I don't understand something because you say that delta is equal to the left side of the very top inequality, right? Like
Yes.
but it is written how many samples to ensure that probability, so that probability is strictly less than delta. So you're saying less is not equal.
Yes, so strictly less basically removes the strict less or equal sign, this one, right? That's the only thing that will change. So, in that case, it's strictly less or equal, right? Because we want the soft max, soft cutoff. That's why you have the equal. Well, in reality, we cannot have 15.27 samples, right? You can only have integer numbers. That's why it's becomes strictly less there. But in this particular case, it's really interesting. How the next one? Alright, let's follow this one, I guess. like this. We move it like this, which then becomes a logarithm.
But do we have to know where it comes from? Don't we just have to remember that number of samples is minus?
No, you just have to remember that formula. We're just going through the steps to see why there was a minus there. Now, hopefully, the minus is because there's a minus 2 here when you apply the logarithm, not because they made it appear in the slide. Alright, moving on from this one. Have a look at the slides. That's basically what the professor mentioned in there. So I would assume it's correct, hopefully.
But do people understand what epsilon and delta represent? Because then it's just remember the formula, plug it in, and be done with it.
So epsilon is decided beforehand, like what we want to achieve, and then delta is kind of the measured accuracy.
So in our case, epsilon would be the probability of our difference. So the difference between our approximated probability and the actual probability is bigger than the error rate. So probability happens more than once in that word, but that's basically what it is. It's also mentioned in the depth. Alright, moving on to the next ones. That was fun. So, as we mentioned, we cannot use rejection sampling because it would take too long. We can use importance sampling, which basically will weight each sample, in a few words, it will weight each sample by how likely it is to happen based on the forward sampling. Now, moving on from the Bayesian networks, we have two simplified models. We're going to discuss the naive Bayes for one sec. Now, why is it called naive Bayes? Does anybody know? Yeah.
Is it because we assume independence?
Yep. We assume independence for the causes, not the effect, obviously. So, for example, if we will look at the naive Bayes classifier, in this case we assume that all of these things, so chill, ache, sore, and fever, are completely independent of each other. And then we calculate the probability. Now, obviously this doesn't make much sense in reality because if you have a fever, you might also have aches, and if you're sore, you might also have aches, and if you're chill, you also might have a fever. Right, so they're not completely independent. But we're assuming independence because they're easier to compute for a simplified model. And the noisy OR gate is basically the reverse of this. We assume that there are multiple causes, and those are independent, and they have the same effect. So, to calculate the actual probability of the effect happening going home, we just combine them linearly via that formula without accounting for dependence between them. So basically they're the opposite of each other, if you can look from the slide. Any questions about these ones? No questions. Perfect. Now, what we can do with Bayesian networks, and this is just a simple application with the algorithm mentioned in the slides. We can, for example, take a list of symptoms, a list of observations. So basically, I have some things I observed in the real world, and I can see, okay, what's most likely to happen, which is what you usually want. So I see these things, and I only care about what's most likely to happen. I don't care about the whole probability distribution and everything else. And you can obtain them via a variation of the variable elimination algorithm using this thing. Now, there's not much to mention about this one, just one application of variable elimination. Now we're moving to Markov chains in decision processes. Yeah, wait, actually.
Do you think the net problem would be in the exam, or is it the low probability?
Well, I mean, I would have to look at the past exams to give a conditional one, but I would suggest just having a look at the algorithm and running it by hand once or twice. It shouldn't be anything difficult. They might just ask you, okay, what's the point of the map problem? Or how do you define the map problem? Or I have a map problem and I just give you the final factors, give me the maximum probability.
He uploaded some extra specific map problems.
Yeah, I thought it was
alongside the
because
practice exams because it's new material, so I'd say the chances of
I thought he uploaded because the answers were incorrect in the assignments, and he uploaded again to fix the answers, maybe.
oh, maybe it could be. But either way, I think it's a new material, so.
Yeah.
There was also the lectures of variable particle filtering or something like that.
Sorry, what?
Particle filtering, there was something in the lecture about, right?
Yes, there should be something about particle filtering, which was mentioned in passing somewhere around here. But particle filtering is basically inference sampling, but you don't take one sample at a time. You take a million samples in parallel and you combine them. Sorry, what? Yeah, Gibson sampling was given in passing as, okay, there are more advanced ways of doing this, but we're not covering them in this course. If I remember correctly, that's what they said in the slides. Because Gibson sampling and AMA, the other name of the sampling, is done during Bayesian statistics, the next course for probability. So anything up to particle sampling might be given with a very, very small probability of anything more than inference sampling at most being given. Because particle sampling, I don't think I saw any exams with that.
I don't think so. I think it would also be quite difficult to do it by hand. I think it's more likely that they ask a theoretical question about particle filtering.
So for particle filtering, just remember what it is, why it is used for, and that should be fine. I don't think they're going to give an application question because I don't imagine you can generate in parallel with by hand. Okay. Any other questions about the probability section? No questions. Perfect.
So next up is Markov chains and that kind of stuff. So I know that it is a lot of maths that seems quite difficult. What I'm gonna try and do is show you that the maths isn't that difficult, and maybe if you think of it in a slightly different way, that it's a bit more intuitive, and then you figure out, okay, this is not that difficult, but it's presented in a difficult way. But before we do that, do you guys want a break of like 10 minutes? Because I can imagine that before we go into the maths, it's nice if you can get a bit of water or whatever.
Yeah.
Then I suggest that we start at 10 to 2, so 13:50 we can take it. It's so weird when the meditation is like before you get to the
Like, you know, it's absolutely not sometimes your mindset to also check the performance. There's also the fact that most of the stuff I just talked about is such a mild but they're social events. Never gonna be fine, just like
No, I didn't.
Okay, could you guys start settling down again, then we can continue.
Yeah.
Okay, so very shortly, we also have Markov chains, as was already introduced. These are a kind of special Bayesian networks, and you will see way more of them and about them and why they're so important in reinforcement learning. But essentially, what we need to know from this is that every state is only dependent on its previous state. This was also already explained in the part about independence. So S4 is only dependent on S3. This is essentially the main thing that we need to know about Markov chains. And you also have that they can be stationary, which means that essentially once you are in a specific state, you will never leave again. But that is basically like Markov chains in short. But then there are also different kind of Markov chains. In some cases we say, well, we can't actually observe what's going on inside the chain, but it does have certain things that it does instead that we can observe. Like, for example, this could be behavior, like I could see my dog doing something, and I don't know what the model in itself does, but I can still observe this, right? And because I can observe what happens, I can get some information about what goes inside. But essentially, that is the main thing about hidden Markov models, is there is an underlying model. We can't directly observe that model, but we can observe the effects of the model instead. So we can also estimate, okay, based on our observations, in what state are you currently? Like, for example, I might say, oh, I observe certain behavior from my dog. I know my dog is likely happy, or I know my dog is annoyed, or whatever. But we may also see, okay, what is the distribution of past states? So then we say, well, given what I have observed so far, how likely is was my dog to be happy? And then we have this path, which essentially says, okay, given our observations, what was the most likely path of the different states that I've taken here? But to be honest, this is all kind of shoved into the course, and I don't think it is that important. The main thing of Markov models you have to understand is that it's only dependent on the previous state, and that we have some special cases in which we can observe something from the network, but not the network itself. Does that make sense to people? Are there any questions? Yes?
So is this just a somewhat accurate approximation of what it could look like in the bottom right corner? Like the Markov model, it always looks the same, right? It's
yes.
Always, except for the values in it, exactly the same.
Yeah.
It just goes on and
yeah, exactly.
on and, or I mean, a long time. And then, do we have the observing things that are dependent on the hidden states? Is that really for every state? Does it have to be, or can it be every 50 states, or never? Or
well, it is really essentially the main thing is what makes your question a bit difficult is that we don't know much about the underlying model, right? It may be that we have many states, it may be that we only have a few. It's both possible, but in essence, the most important thing is to understand that there is a hidden part of which we can only infer information by looking at what we can observe.
Yeah, so basically we just have a very low-level understanding of this in this course, and we just don't need to know more.
Yes, well, that's kind of the essence. In reinforcement learning, you will notice that, hey, this is really cool, and oh, this is so useful, and here it's kind of like, you know, this exists, but...
Yeah.
Could you explain more what is stationarity?
Yes.
Or
It's stationary. There's no outgoing arrow. So, once you get into here, then there's nothing afterwards. Yeah. That's it, basically.
Okay.
Yes?
What kind of version you can expect from hidden?
Rosvan, do you have any idea what people can expect for Markov models?
I asked them instead if you don't have to compute anything, so just know what they are.
Okay, that's nice to know.
No, I don't know off the top of my head. Maybe there's some in the old exams. Then the next thing is that we have utility and preference. So the entire thing about this is certain states have a specific utility, right? We would rather be there. So like say we have a state that is you fail your exam. I would hope for everybody that has a low utility, right? Essentially that means I don't want to fail my exam. But on the other hand, the state where you pass your exam may have a much higher utility, right? And the main thing is your utility is based on your preference. So every person may decide, oh, passing this course is not that important, so the utility is lower. Or people may say, I must pass this course and the utility is higher. This is all... What the fuck? What? How does it... I am a bit of a boomer. But, okay, so back to preferences. It's kind of important that we start at thinking about what is preferences. So there are a few different cases. We have this up here. This just says, I prefer outcome B over outcome A. Or you can say it doesn't matter. Or I don't prefer outcome B over A. Or something that you should also keep in mind is something, if you have this. So here we say we prefer A over B. And we also say we prefer B over C. Then we should also have that this is the case. Because if this is not the case, then we get stuck in the loop, right? Because then we can say, well, I prefer A over B, which I prefer over C, which I prefer over A. And this can get you in very weird situations. So I think in the slides they say, well, A can be, you give me money, B can be, I give you back a bit, and then etc., to the point where you lose everything. So it is important to keep in mind that this is what we want. And this is called transitivity, which you may have seen in other branches of maths. It's not really important to know what it's called, it's more important to know that it's a thing. Okay, so what we then have is we have something that's expected utility. So that's given an action, what can we expect to come out of this? So let's assume, so we go back to our example, we have our outcome of study. So we have our action of study, and we have our result, which is pass or fail. Right. So again, our results all have a different utility, right? Depending on our preferences. So I will say, I give this a 10, and I'd rather not fail, so I give this a 1, right? So then what we can compute is, well, or we want to compute the expected utility rate, and then what we see, this is a sum over all possible outcomes. So what we say is, so we sum over study. So what we say, okay, we want to know all the sums of studying, what can happen, right? There are two options. Either we study and we fail, or we study and we pass our exam. So we can say, well, if we say pass given study, and then is this readable, by the way? Okay. So essentially we say we have two different probabilities, right? We say, well, if we study, then we have a 90% probability of passing, but still 10% of failing. Then what we do is, if we compute the expected utility of this, then it's, in this case, 0.9 for this probability. Times 10, which is the utility. and then plus. This is our expected utility. Does it make sense how we got there? This is essentially, and let's ignore the sum. This is just a weighted sum of the different outcomes in the case that you study. Now, what we can also do is we can also do this, but for not studying, right? And then we get another expected utility, and what we hope is that that expected utility is lower. In that sense, what we then want to do is we want to maximize our expected utility, right? So we say, okay, what action do I have to take to get the most utility? So what steps do I take to get the action I prefer the most? So that is essentially what you do. You just compute your expected utility for your different actions. You get the utility, you just pick whatever is the highest. Are there any questions about that? So then we have another kind of Bayesian networks. We have decision networks, where we have decision and utility nodes. And also we're gonna soon talk about a policy. And a policy, I know it sounds very scary, and it may look very scary if it's written in maths, but essentially it just means if you're in this state, do this. If you're in that other state, do the other action. Like, it's very simple. It's basically an if then for everything. And again, the goal of this policy is to maximize our utility. So we're looking for the steps. For every state, what do I do to get the highest outcome possible? Now we have different nodes in our network. We have random variables, we have decision variables, and we have utility nodes. These you can't influence. These you can influence. So this is the point where you have to make a choice, which in our case, this is studying, right? If you study, you can decide that for yourself, but we can say random variables, how difficult is the exam? Like, are there any questions that are purposefully put in there to fuck you over, yes or no? Well, that's unfortunately out of your hands. But whether you study or not, that's not. And then at the end we see we have a utility that combines all the information in the network and it gives you just the result. And it just looks like this. Now, what's interesting is there are no distributions for the decision nodes. That's just whatever, basically. But for the random variables, there is a distribution. And again, we can use variable elimination here, which is we just construct this. Now, there is also another table that is for the utility that's not included here. It's included in the slides, if you want to get the complete picture. But essentially, we can compute this factor here, right? And the next step, what we do in variable elimination, is we just sum out all the random variables. And then we're left with, well, our policy, where we can see what is the best decision to make. And what the best decision is purely, we look in here and we see what has the highest. And then obviously accident is gone, but you just look, okay, what has the highest utility, and then this is one of your decisions, and that's the other decision that you have to make. Are there any questions about this?
Then how policy would look like in this example?
So a policy would just be where you say, at the start, you just say, okay, for the optimal outcome, you take, for example, the shortest way and you wear your pads. Does that make sense? You still seem confused by something.
Yeah, I don't see all of the numbers.
Oh. Well. Cool. Then we have something called Markov decision processes. And this is already getting a bit trickier because in the previous steps what we've kind of assumed is that if you make an action, it's actually going to make that action, but in reality that may not be entirely the case, right? Here it is, if you want to move in a specific direction, you still have only an 80% chance that you actually go in that direction. So there is a bit of randomness here, and this will also influence the way that we create our policies, as we see later. But for now, this is not important. For now, we're just going to get some terminology out of the way. So hopefully the maths that we will see in a bit doesn't seem as scary, hopefully. So we will start with our states. Essentially, every square that you see here is a state that we can either be in or we're not in. You have a set of actions. So, for example, in this state, you have an action that's move up and move right and move left, also implicitly. But then what we also see is that we have a transition matrix of probabilities for t. So we say, well, given that we are in a specific state and we take a specific action, what is the probability that we end up in another specific state? And then we have a reward. So essentially, this is how you can control how your system works, right? We say, this has a reward of 1, this of -1. So in this way we say, well, if you get here, that's bad. If you get here, that's what we want. So you get some reward for it. And again here, we try to find a way to move throughout this maze or this graph, whatever, to maximize the sum of our rewards. Does it still make sense what we're doing here? Any questions about the terminology? Because if there is any clarity, it's nice to get it out of the way now before there is more crap thrown in. Cool. Because then we get into the Bellman equations, and I think for a lot of people this looks rather intimidating, right? Okay, cool. I'm glad we agree with that. Let's start with just thinking about what we can do. We can say, well, okay, every state has a certain value, right? There are states that we would rather be in, and there are states that we would rather not be in. That's essentially what we just say here. In this first equation is we're going to define a value for each state. So that is the numbers that you see up here, like the 0.705. That's just the value of that state, right? Unfortunately, often we don't know all the states. But what we do know is, okay, we currently are in a certain state and we can take a certain action. So instead of defining the value per state, we can also define it per state and action pair, which is what we do here. So
what do you mean by certain state?
Certain state is just like one of the squares that you're in. Does it make? Like, okay, you have states, right? That you are either in or not. In this context, is any of these boxes is one state. So this is a state, this is a state, right? Yeah, and then the directions in which you can move are all your actions. And what we can see is that they're different per state. So that is what we do in this formula. Don't worry, I'm going to explain the formula step by step later, but first I want to kind of sketch out the reason why we're actually interested in doing this. So the alternative is that we say, okay, we're going to look at the state transitions instead. And then the alternative is, so this is really about the actions, right? These. Okay, I'm not entirely sure whether those V and Qs are correct. I'll take a look at that later. The other alternative is that we just look at the transitions and we give those a value. Like if you have a transition, say, from this state to that state, then that transition itself can have a value, right? So now we're no longer looking at the value of this state, then we're looking at, okay, what is the value of if I move to that state? And again, we can also do that for the state and the actions combined. So then finally we have a discount factor gamma, which is essentially something that you multiply by. So the entire idea is we want to make sure that our agent doesn't stay within this maze forever. We want to force it to move to a certain outcome. And by giving that gamma factor, we can do that. So what we actually see is, if we
move this. So roughly what it will look like is you have an R. This is just your reward at the first time step. So that's essentially it goes on like this, right? So every step we multiply by another factor of gamma. So what we see is that the first few steps are relatively, or well, they're significantly more valuable than the later steps. Assuming that our gamma is between 0 and 1, by the way. Because if we think about it, can people tell me what it means if your gamma is 1? Yeah? Sorry? Sorry?
Every future state is equally weighted?
Yes, exactly. So what that also means is that we don't have a preference for how long it takes. Like, we could say, well, you can just run into in loops. It doesn't matter. But if we have it lower than 1, we say, well, eventually, if you first do like 20 laps around the middle block, right? Then once you get to a result, it's going to be completely worthless. If it's above 1, we also get interesting behavior, because then it means that every extra step that I can take in a maze will give me more reward. So there is no reason for me to finish. So that is really why it's important to have it between 0 and 1. Okay, so then I guess we go on to the scarier maths. Is if we calculate the value for a given state, that is just the value of that state itself. Okay, that's still simple. And then what we do is we do a weighted sum over all its neighbors. So if we write that out, what the first formula says, and I'm starting at the bottom left here. This is just its own reward, right? This is already defined. And then we do a sum over S prime. By the way, we say that usually what we do is we write the policy as a pi. What this means is what is the value from state 1, 1, 1 if we follow policy pi from there. So this is essentially what the formula says, right? So if we write this out, then we can have this. So then we have the probability of that we move to the state above, which is 0.8, I believe. And then we multiply it by So if we write it out, this is what it comes down to. Now this is interesting that this part has the same value as 1, 1, right? The reason for that is if we try to go left here, it's not possible, so we just remain in this state. So again, all that we've now done is we've just written down the weighted sum. So the value of a given state is the value of the state itself, plus the value of the state that it can reach in one step, so its neighbors. And then we still have this gamma term here. Usually what it is, it's set at like 0.96, but usually, and I would imagine for your exam as well, it's just a given. So are there any questions about how I got to this?
There's, for example,
that is from the transitions in this picture. So in top right. Because then I say.
Transition with,
Sorry?
what denotes transition? Like, what is the letter that denotes transition?
The T.
Is it D? Or
Yes. Yes. Take a look at this. Nah, it's a probability, but
With 0.8, you have the chance if you go upwards, the chance is 0.8 if you really go upwards. And there's also a chance that it might go left and right randomly of 0.1.
yes. So essentially, what we do is we count for from this state all the next states that we can reach as well. Yes.
If we don't have any numbers given, should we then infer the number based on we start with 0 and then all the steps times the discount until
Yes. So there is an algorithm that we will see on the last few slides that kind of goes into that. But that's for later. I think for now we're slowly building.
So in this case the numbers will always be given already.
Yes.
But in the formula, first one, right? First row.
Yes.
State formula. So I don't see probability in that formula. So where is it coming from?
What in this formula?
So it's D, but in the previous slide it was denoted as B. So that's why I'm confused. Okay, now I see.
Okay, cool. So, but it's also the case that this is not entirely complete yet. We would also have to look at, okay, if we move to the right here, right? There's a right. Because from this state we can either go up and hopefully actually go up, or if we actually want to go to the right, we can also do that, and we could also end up in the state itself again. So these are the options. What we see is for Q it's slightly different, because there we actually really take the action into account. Yes?
Okay, you also move down and then have the chance to go right.
Well, in our model we have defined the transitions as that is not possible. But of course, there is theoretically no reason why that shouldn't be possible. It's just that the way that our model is set up says you can't. So it's important. It's actually a good point that you bring up. It's important to just make note of what the model actually says that you can do and the way that the probabilities work. Because usually it is the case that from a given state you can reach multiple other states, and then you just want to have a weighted sum of the utility that you can get from all those states. For the other ones, the calculations are really similar. So I would suggest that you take a look in the slides if you want to have a more in-depth explanation about those as well. Yes? What? Yes. Yeah, so essentially the 0.8 is just in whatever direction you want to go. Yes. Did you also have a question?
Yeah. So there's the specific state rewards and there's the position rewards. And do we know if both will show up, if both are important to know for the exam?
Well, I know when I took the exam we had to use the Bellman equations to calculate the value of a given state. Which is not super difficult, it's just really tedious. But this is more something that is kind of part of a different algorithm, right? We've now kind of gone through the underlying maths and hopefully you've gotten at least some feeling for what it's trying to say. But then we have value iteration, and then we also get to the point where what if we don't know the numbers, right? Then we just initialize them at 0.
Can I ask what is Q in the previous slide?
This one?
Yeah, in the second equation.
Yeah, okay. I'm quite sure that this is a typo, that V is for the values for a state,
Yes.
or is because here we define the value for a state, here we define the value for a state and an action, here we define them for state transitions, right? So we define it for something else.
Mm-hmm.
So V is for the states and Q is for the transitions, I believe. But it may be that this is a typo, so I would check the slides just to make sure.
But here on the pictures, we're having the values for the transitions, right?
No.
We've got only values for the fields.
Yeah.
Okay.
But it's just in terms of, you know, it can be that they are defined in one way, it can be that they're defined in a different way. It doesn't really matter because the ideas behind it are similar. It's just your numbers come from somewhere else, so we give it a different name.
Yeah, of course. Okay.
Yes?
So the number on the field is the more associated with the field.
Yes. But what we see is once we compute this entire sum, this is going to change, right? And if this changes, then it means that it should also change for all other fields that can reach this certain state. So essentially the problem with this is if we want to estimate this perfectly, we have to do infinite many repetitions of this entire process. That's really time consuming and impossible. So what we say is, okay, we're gonna stop if it doesn't change more than a given epsilon. Like we've previously seen, epsilon is usually a very small number. So we say, well, if it doesn't change more than this over like 2 iterations, then we just say we're done. That's good enough. So this is, again, we just start filling in everything with a 0. Then we use our Q values that we currently have, so those are of 0. And then we just plug it in here. And then what we see is once we have our Q values, right? This is about the state and the actions, I believe. Then we can update the value for every single state. And then, again, what this just says, if the change for any given state is bigger than our threshold, we do the entire thing again because we're not, we haven't gone to the optimal point yet. And then at the very final step, we create our policy. And again, our policy just says, if I am in a given state, what action do I take to get into the next state that has the highest value, right? So if we are in this -4 here, and we can say we can move to the left, to the right, and up, then we can say, well, in our policy, we want to move up or left because those have the highest values, right? So essentially the entire goal of value iteration is to get to the point where you've filled in the square, you know the or estimate values of the state, and only then you start to make your policy. And your policy is just really simple. Again, it's you are in this state, do that. You are now in that state, do that. It's nothing more than that. Yes.
And you would get the policy because in the, like for every iteration to update the value, you always take the maximum, so the value of the best action, right? So then to get the policy, you look at what values you or what actions you use to update the values in the last iteration.
Essentially, this is a for loop, right? And 5 only happens at the very end. So once we get to convergence, right? Once no state value changes too much anymore, then we say, okay, now we're done. Now we have, in this case, this entire grid. And then we're just gonna look for every state, what action do I take to maximize my return. Does that make sense? So it's really update the values first, determine the policy afterwards. Do you have a question?
Yeah, it was just the goal that we already and that does
mentioned to maximize my return in the end, then you kind of trying to get back to the initial state, or?
No. So again, our policy really is you are in a given state, what action can you take to get the highest utility in the next state? Right? Because we can say, well, this is a value, this is a utility, it doesn't really matter what you name it, like the idea is the same. The point really is how do I get the most of it? What steps do I take? And that's your policy. Like your policy is basically at every single point, every single choice you can make, it tells you you have or you should make this choice to get the best result. Yes?
For value iteration, have you actually seen any examples of that on the exam? Because all the practice questions have always been policy iteration with rewards on states.
Mm.
So the rewards on transitions and the value iteration I haven't seen in a question yet.
Well,
is it
essentially, I guess the ideas are really similar, right? That helps. Off the top of my head, I can't remember whether I've seen them or not. But the main thing is you kind of have to have understanding of why we do it in this certain way. And I think if you know it, you can probably also come up with it during the exam. But what I have seen is that there's like, you have the Bellman equations and it's, calculate the values for this and that state. That is a question I've seen, or it's some policy evaluation, like you do 2 steps. But besides that, I haven't seen this exam. I haven't seen many of the exams of the previous years, so I don't know. But again, we have policy evaluation or iteration. So here we just start with a random policy, right? What does a random policy mean? Random policy may look if we have a grid like this. It may say, we go down here, we go that, we do this, we do that, we do that. Something like this, right? Now it doesn't matter whether it's complete nonsense or not, because it's just our starting point. What we then do is we just evaluate the value for each state if we follow this policy, right? Then all the values from the states are updated, and then maybe we realize like, hey, hold up, our policy doesn't actually match what the values in my state system say. Like it may be like, I don't actually reach this state that has a really high value. Instead, I go to this state where I lose a lot of value. That's weird. So what you then say is, okay, wait, hold up. I've updated the values of my states. Now I can update my policy again to incorporate the new changes to the states. But because you update your policy, the values to your states may change as well. So you kind of have this feedback loop. And again here, we repeat this until the policy is stable. Now, what does a stable policy mean? It means that in this case, these arrows do not change anymore between iterations. Because it may be that we say, after the first iteration, we say, well, actually, hold up, this arrow should go that direction, right? So this wasn't stable because we made a change. Now, it may be that we do another iteration, and then it turns out this doesn't change anymore. At that point, we know, okay, it's stable, and then we can just stop. And the nice thing is we now have a policy, right? Because for every state, we say, move in that direction, move in that direction. So that is the goal of policy iteration.
But how do you know that the policy will be stable? Why can it not be unstable forever?
Well,
I mean,
okay, so there is probably a really nice mathematical proof that will take ages to figure out. But essentially, it's, I think, if we look at this, right, it says we follow pi, that's our policy. If our policy doesn't change, then the values of our states don't change either. Does that make sense? So then we kind of get into the point where every iteration our policy doesn't change because our policy doesn't change, the values don't change because the values don't change, the policy doesn't change. So I don't think there is a point where you can get an infinitely unstable policy.
Okay.
I think it's really in the way the Bellman equations are set up and the way they update themselves is really set up to, you know, it may take a long time, but we're eventually going to converge to the true values. Are there any other additional questions? Yes.
So it's basically like the first one, the evaluation, check if something changes, and then when nothing changes anymore, then we retire the
Well, so, okay, the main difference is, here we only compute the policy at the very end. Here we compute the policy at every iteration. Yes, so essentially, here we do two things at the same time. And there are certain drawbacks and benefits of both approaches. I don't really know them off the top of my head, and they're not that important. But that is the end of the slides that we prepared. Are there any other specific questions that people have? It can also be any exam questions that you would like to discuss because we're here now. Because if not, I guess we're done. Oh, yes? Yeah?
In one of the questions of the exercises, there's one with a Bayesian network given, and the question is how many numbers have to be specified. Like, kind of, I don't really get it. I don't get what number.
From the
Specified for what?
I don't know. It just says how many numbers have to be specified in the Bayesian network.
Well, you do need to know, as we discussed, for Bayesian networks, each node has like a table of values, right? And you need at least those values to be able to influence the network. So you have to go for each node, see how would the table look like, count, you know, the number of spaces in that table, and sum them up together, and that should be the answer. So for example, if you have like the example network given in the slides, you have the independent values which have just two values, right, each. So you need to specify one of them, right, because they're binary.
Why one?
Because they're binary, so if you know one of them, you know the other as well, right? So if you don't, that's for example, that's what I meant. So you need to know for P of A, you need to know whether it's true or false. For P of B, you need to know, again, two of them, right? Because you can deduct them with two. Same for the others. So those sum together. I mean, I imagine that's what they're asking for.
I remember in Discord how that number of probabilities in conditional probability table that was not clear what needs to be specified.
Sorry?
So the number in the question. So number.
Yeah. So
number of probabilities in conditional.
Yeah, that's what I meant. So the thing is, since you have this only works for binary variables, there is a general formula for them, but for binary variables, you usually need half of the values in the table to be filled in order to be able to tell the other half. Now you can get any half of the variables, but you need half as in half the number.
Cool. If there are no further questions, then thank you for your attention. I hope you all ace your exam.